It's the middle vertical. All right. Our last bit of information for section 3 is talking about valence electrons. And what a valence electron or electrons are is essentially the electrons in the atom's outermost orbitals. Or in other words, the electrons associated with the atom's highest principal energy level. I'm going to give you another little thing you can write on here. The valence electrons, for the most part, come from the s and p orbitals. For the most part, what we're really going to be focusing on. Okay? Some could come from the d orbital, but we're not really concerning ourselves with that at the moment. Okay? Now, we look at sulfur. And we did sulfur's electron configuration using the noble gas version. We find sulfur has a electron configuration of Ne, 3s2, 3p4. Sulfur contains 6 valence electrons. How did we determine that? How did we get 6 from this electron configuration? What's that? Add the superscripts. 2 plus 4. You get 6. Cesium. Electron configuration of Xe6s1. It only has 1 valence electron. And again, we find that out by looking at the superscripts on the S and the P. Again, transition metals, lanthanide actinide series, they're going to be a little different in terms of their valence electrons. But we're mostly concerned about the outermost principal quantum number, and that's where S and P reside. That's why we focus on S and P. These valence electrons are what will eventually determine the chemical properties of an element. You also want to know another way to figure out the valence electrons for a good chunk of the elements. Get out your periodic table. Ooh. Again, you should have a periodic table that looks like this. Do you have that one? Do you have one that looks like this? Or do you have a periodic table at least in general? Let's see which one yours looks like. Okay, well, I'll help you write this one. We'll use this one for you to make a little additions to your current periodic table. Okay? All right. Did everybody see this? Barely. You see this back there? Ish. You'll get the gist of it. I'll zoom in a little bit. All right. So another way that we can look at and determine the number of valence electrons for an element is this. You look at this first row right here. See where I'm at here? What number do I have above that column? U. 1. That elements in that column have 1 valence electron. So if you want to put the number 1 here, go ahead. Look at the next column. All of these in this column. What number is above that one? 2. Each element in that column have 2 valence electrons. You start seeing a trend here. But We are, like I said, we're not concerning ourselves with the transition metals, so we're going to hop across the pond and look at the P block. What I want you to do is above boron, write 3. Above carbon, write 4. Above nitrogen, write 5. Above oxygen, write 6. Fluorine, 7. And helium, 8. With an exception. Helium does not have 8. Helium has 2. Okay? But everything else in this column has 8. Okay? So helium has 2, but neon down has 8. So again, you don't always have to do a electron configuration to determine how many valence electrons an element has. You get the shortcut method. So now that we know what a valence electron is and how we can determine that in a couple different ways, we then get to what's called an electron dot or Lewis dot structures. You also hear them called Lewis diagrams, just straight dot structures, electron dot. They go by a handful of different names. But specifically, they're called Lewis dot structures. Okay? And what these indicate are an element's symbol surrounded by the number of valence electrons for that symbol utilizing dots. Those dots, again, representing the valence electrons. Now, there's no set guidelines on how you do the dots, but there is a general practice. If we were to look at a symbol, there are 4 sides to a chemical symbol. You typically do pairs, or 2 and 2 and 2 and 2. So you never want to exceed 2 electrons per side. Okay? So there are a few steps that we utilize to draw a Lewis structure. This will probably be the easiest thing you do maybe all year. First, it should say, first identify where the element is and its symbol, but it says determine the number of valence electrons for the particular element. Then you're going to write the symbol of the element, which represents the atomic nucleus as well as the inner level electrons. You'll then surround the element with the valence electrons so that each of the 4 sides gets 1 electron first, and then you can start pairing them up as you see fit. Again, it does not matter what side you start on. If you have extra valence electrons, then you start placing one on a side until no valence electrons remain. Again, it does not matter what side gets 2 electrons. Me personally, I'm all about symmetry, so oftentimes when I do them, I try to make them as symmetrical as possible. You don't have to do that, but it's just a thought. So we're going to do a few examples, and then you're going to be working on your homework. Your homework will be turned in tomorrow at the beginning of the class before you begin your homework check. Everybody got it written down? Let's look at a few examples. Magnesium, sulfur, and bromine. Okay? So I've already taken the step here and written the chemical symbols. So we got magnesium, sulfur, bromine. why it's very important to have a periodic table. All right. Now, do you want to do the long way or the short way when we determine valence electrons? Probably will do the short way, don't you? Okay, so what column is magnesium in? Second. So how many valence electrons does it have? 2. So again, you could do this any way. You could do it like that. You could do it like that. You could even do it like that. It really doesn't matter. Even though the rule said you want to try to at least get one on each side, it doesn't matter. It really doesn't. As long as you have the correct number of dots to represent the valence electrons, that is fine by me. Okay? Let's go to sulfur. What column is sulfur in? How many valence electrons does it have? 6. So again, if we go and do it by the guidelines in your notes, 1, 2, 3, 4, 5, 6. And lastly, bromine. What column? So therefore, it has 7 valence electrons. 1, 2, 3, 4, 5, 6. Oops. 6, 7. Now, as you're writing that, what are these useful for? Besides showing, the number of valence electrons. When you are trying to illustrate what's happening in a chemical reaction, the use of Lewis structure. In fact, we're just getting finished up with this in my honors class, where we go a little further and do the Lewis structures of molecules and demonstrate what's happening in a chemical reaction, where the electrons are going, who's forming multiple bonds. It gives you a visual representation of what's happening in a chemical reaction. Who's being kicked off of a molecule, where's it going, who's it joining up with, and who's replacing it as products are being formed. Okay? It's a lot easier to see a Lewis structure in what's going on than it is to see just chemical formulas. But, once you have enough practice with chemical formulas, you kind of get the gist. But that's why Lewis structures are nice. We get to see the actual movement of electrons and who they join up with to form bonds. Okay? Again, this can go quite a bit a step further. We can even do ions with this as well, where we kind of have to do a couple of additional steps. Anyway, that is all for our notes. I think that is all for our chapter. Yep, chapter is done. And so I'm going to stop this recording, and then I'm going to hand out your homework.